In this section, we will be taking a look at other common functions, and the first type we'll be looking at will be of the form ax to the n. So let's have a look at one with odd exponents. You remember the identity function, f of x equals x, is a straight line at a 45-degree angle that passes right through the origin. Okay, this is kind of a parent function. Well, so is this one, f of x equals x cubed. X cubed functions always make this curved shape like this. Now, of course, if you add some other things in here, what goes on in the middle could change just a little bit. But in general, x cubed will make this S shape. It would start in the third quadrant and end up in the first quadrant. Okay, the same thing is true for x to the fifth, but what I want you to do is compare these two. Compare the middle part of x to the fifth to the middle part of x to the third. Do you notice how it gets a little bit flatter right in the middle? It gets slightly closer to the x-axis at this point. It also gets a little bit steeper. So it's steeper here in both directions, and it's flatter in the middle. So how about even exponents? You remember your parent function, f of x equals x squared. That's your quadratic function, and it makes this nice parabola. Well, compare that to a function with the highest exponent of 4. It's still the same general shape, but it gets flatter in the middle. It gets closer to the x-axis here. It also gets a bit steeper as it gets taller. Same thing is true for x to the 6th. It gets even flatter in the middle than the x to the 4th does, and it gets steeper quicker as well. Sketch the graphs of the following functions. So we have f of x equals x to the 4th divided by 3. Now what I have here, I went ahead and put the Hawkes Learning System statement. What it's telling you is that since this is multiplied by, maybe I should change that back to black. Since this is multiplied by a fraction, 1/3, remember what we talked about in the previous section? If this is between 0 and 1, it's going to stretch it horizontally, or it's going to compress it. So it's actually going to make it short and fat. So it's just like that x to the 4th function, except it's going to be a little bit wider because it's getting compressed. So we do know that much already, and they went ahead and found f of -1. So they just put a -1 in here, raised it to the 4th power. That would be 1, and 1 times 1/3 is 1/3. Then you try f of 2. Well, if you put a 2 in here, 2 to the 4th power is 16. And 1/3 times 16 is how they got the 16/3. So once you draw this graph, it looks something like this. So as you can see, it's flatter in the middle. It's compressed a little bit, so it's a little bit fatter in here. And we've plotted those 2 points that we have found. How about this one? F of x equals -x to the 5th. So we know that this function is going to have the same shape as the function f to the 5th. Remember, that's that S shape that we had earlier. But it will be reflected across the x-axis because it has a negative here. So earlier we were talking about how x to the 5th is something like this, but it's a little bit flatter in the middle than the x cubed function. Well, if you were to take this and flip it over the x-axis, just flip it over, you would end up with a function that looks like this direction. Of course, it should be a little bit flatter in the middle. So that's what it's going to look like. And then they went ahead and found a couple more points for this one too. If you put a -1 in here, you raise -1 to the 5th power, you get a -1, but you still have this negative in the front. So a negative of a -1 is how they come up with this +1. Well, what if you put a 1 in there? 1 to the 5th is 1, but because there's a negative in front, you get a negative 1. So if you were to graph that one, it would look something like this. So how about functions of the form a over x to the n, where you have odd exponents on that variable that's in the denominator? Well, we are going to be talking more about this type of function in chapter 6, so we'll just briefly talk about them here. Your parent function is 1 over x. It will look like this graph here. As your exponent gets larger, notice how the graph gets closer to that x-axis, and it gets a little bit more flattened out in this area. You can also tell that your graph doesn't seem to be quite as steep as the original one. So it gets a little bit less steep each time you increase that exponent. Same thing is true here. Notice the difference between these two. It's a little bit closer to the x-axis, a little bit flatter, and not quite as steep in both directions. So if those exponents are even, your graph changes and looks something like this one. But the other patterns still follow through. This is still closer to the x-axis, it's still a little bit flatter, and these are still not quite as steep. Notice the differences in these two. Same thing applies. A little bit flatter, closer to the x-axis, and not quite as steep going this direction.